Hello, once again. Good morning, everybody. Welcome to the second presentation on implementation of LLMs. For those of you who joined the session, my name is Igor Lubashenko, and I'm the chairman of this session. So today we have a presentation by Timo Rohner. The challenge of identifying and filling content gaps remains crucial for many organizations, I guess, and today's presentation offers an innovative technical approach to this problem. We will discover how advanced encoding techniques and synthetic data can create more robust content and strategies. Timo, I'm giving floor to you, but maybe before that, just a reminder to our guests that you are welcome to provide any comments and ask questions in this window next to the transmission, and I will try to moderate everything and transfer your questions to our presenter in the end of this session. So, Timo, the floor is yours, please.
So thank you very much for the introduction. As you mentioned, my name is Timo. I'm the director of AI at Shelf, and I'm going to be speaking today about detecting content gaps using crossencoders and synthetic data generation. So the agenda is relatively simple, right? So you have the title of the talk here. First, why do we care and what is a content gap? Then why crossencoders? Why is this our approach? What challenges have we faced? And then why do we bring synthetic training data generation into this whole problem? And specifically, how do we leverage synthetic training data generation, and what is the impact of actually using that training data generation? So what and why? Why do we care about content gaps? So first, a content gap is simply said content we want but don't have, right? At Shelf, this is specifically in an enterprise setting. We deal with a lot of unstructured data from more than 100 customers. Think of, Confluence, SharePoint, all of sort of the documents, PDFs that you have within your organization, from technical documentation all the way to HR policy, parental leave policy documents, and things like this. So the question is, what do we want, but we don't have yet? And the reason we care about those content gaps, especially now with Gen AI being so popular, and having chatbots and LLMs, and we do RAG and all of these things, right? Especially in enterprise settings. If we have content gaps, we get bad answers, right? Chatbots, especially LLMs that are trained on public data sets, they cannot answer questions that require special knowledge that doesn't exist within your knowledge base, right? The example here is, am I eligible for parental leave, right? Especially in a country like the US, for example, that might heavily depend on the specific company policy, since there's not, let's say, universal parental leave policy. Similarly, it might depend on, how long you've been at the company, for example. And if there's no document covering that, and you ask a chatbot or a support chatbot that uses an LLM, it will not be able to really answer this question to you. And even worse, maybe it will not tell you, I don't know the answer, but it will confidently give you an answer, right? And since there's no document that can be used to ground the LLM, we will get a hallucination, right? So in RAG settings, retrieval augmented generation, we try to take content, feed that content to the LLM, and then the LLM should not invent anything, but instead use the content that we've provided to provide the correct answer. And then outside of a Gen AI context, it's even more obvious, especially in a work context, right? We have employees. Employees need to know certain things. Ideally, they should be able to look up those things. You don't want your organization to be an organization where every question requires a meeting between two people to explain something. Certain things should be on Confluence, on SharePoint, whatever platform you use for your knowledge base, right? So being able to tell customers in an enterprise setting, hey, you are missing this piece of content, go write it, is a very valuable business proposition, business value for them. So more specifically, what does this content gap look like? And here's sort of how we can conceptualize this in a diagram. So within all possible human knowledge that has ever been created and will ever be created, our content universe, there is some content that exists within our knowledge base, right? And some of that content is relevant, some that is in the knowledge base and some that we haven't captured yet. So we have the intersection of those two, which is the relevant existing content. And then we have the relevant non-existing content, labeled here in green. And those are our content gaps, right? It's content that is relevant to our organization, our company, our department, whatever you define as relevant context here to be. But we don't have it as existing content in our knowledge base yet. So how can we find out what's in this green part here? So this green part here is basically the relevant content minus the existing content. And the existing content is very easy to define, right? You just ask yourself what content is in our knowledge base. For the relevant content, it's a bit trickier, right? Especially for the relevant content that you don't have yet. How do you figure out what content is relevant, but you don't have it? And there are two questions you can ask yourself here, which are, what are users searching for? And what are users asking for? So what are users searching for? That's, what are users typing into the search box on Confluence, on SharePoint, right? Or any other software system you have. And then what are users asking for if you have an internal chatbot, or you have a Slack channel where people can ask HR-related questions, anything of that sort, where users can interactively ask open-ended questions. That's a good idea for what is actually relevant within your organization, right? Whatever users are asking for, what they're searching for, is a good proxy for relevance, so for relevant content. So we have the user search queries and any sort of chatbot or agent conversations. And this can really help you nail down what the relevant content is. So on a high level, that's how we define content gaps and sort of like how we can get to those content gaps. So here's the proposition for a very basic algorithm of how you could now identify these content gaps, right? So on the left here on top, we have the inputs to our algorithm, which is like, let's say a search query, right? Which is a proxy for relevant content, because if people search for it, most likely it's relevant content. And then also we take existing content and we feed it into some algorithm or model. And as an output, we'd like to have either a thumbs up or a thumbs down, right? They match or they don't match. And then we can come up with sort of a pseudo code algorithm. I wrote it here more or less in Python syntax, which is that, first of all, we don't have a match for a search query. We iterate over all the content. If our algorithm says that the search query and a piece of content match, then we have found a match, right? Found match equals true. And we can end. And as we loop through that, once we've looped through all of the content, if we still haven't found the match, well, then we have a content gap, right? So then we can print, oh, our search query is a content gap. Or we can store it in some database or whatever you'd like to do with it. So the question is, can we come up with a good algorithm or model that sits here in the middle, that takes as an input search query and content, and then as an output says, yeah, either it matches or it doesn't match, right? And the easy or naive approach would be to just use some similarity method, right? Semantic similarity. So the way this usually works, right, is we have the search query and we have the content. We use some sort of, let's say, BERT style encoder model, anything transformer based these days, right? And we produce embeddings for both the search query and for the content. And then we use some similarity metric, right? So cosine similarity or the dot product. And then based on whether the result is above a certain threshold, we say, okay, those things match or they don't match. Now, I've labeled this on top as the naive way. So obviously there's something wrong with it, right? Obviously there's some edge case where it doesn't work. Otherwise I wouldn't call it the naive way. So what actually happens in reality, right? So let's look at an actual example of content that you might have in an enterprise setting, right? So first of all, here on top, we see our search query, which is free ship 50, which is a promotional code within, let's say, an online store or some website that sells products. And then part of their content in their knowledge base, they have some information about those promotional codes, right, where they explain how those promotional codes work. And they say to encourage customer engagement, blah, 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 right? And we see that this free ship 50 is a promotional code for free shipping on orders over $50, right? So obviously these two things match, right? If someone is interested in this free ship 50 code, there is content that exists that is relevant, that explains what this code does. It's for free shipping above $50. You don't need to do any additional content creation. This is well defined, right? And the problem is if we use this naive approach of just creating embeddings and then comparing them using the dot product, what we find is that we see that this is considered 35% similar, right? Or 34.9%, right? And I actually ran this through BGE M3, which is a very modern, I don't know if it's state of the art, but it's a very capable semantic similarity approach. And the main reason this doesn't work that well is that when we produce these embeddings, we abstract away all of the nuance, right? We need to fit this whole piece of content here that talks about plenty of other codes, right? Like welcome 10. We need to fit all of that into a fixed dimensional vector, right? Some of the nuance, some of the specifics will get lost when we do that translation. So when we have this very specific search term, free ship 50, it will not be captured as actually being the same thing. And from this, we might infer that we actually have a content gap, when in reality, we don't. So what's the solution here? The solution is, instead of using this approach, we use a cross-encoder, right? And in this case, I'm using the cross-encoder from the same people, right? This is the BGE re-ranker M3. So under the hood, they use the same training data, right? Very similar architecturally. The only difference is, instead of having it more be a embedding-based similarity approach, here they implement it as a cross-encoder. And we see that, you know, without any changes to content, right? I throw the same exact search query with the same exact content in, and I get 95.7% similarity. So why is that, and what are the differences between the two approaches? So the first example, right, of just the naive way is we have our encoder, right? And this can be the same encoder here for both. And first we feed the search query in, right? This free ship 50. You know, we tokenize it, we run it through the encoder, and then the encoder gives us the hidden states of all of the tokens. And usually this depends on the implementation, right? We take the first hidden stage of the classification token here, right? And this is our embedding. And then we do the exact same thing for our content, right? We run it through, we tokenize it, we run it through the encoder, can be a different encoder, can be the same encoder. And we also get our hidden state here from the classification token. And then we do the dot product, as I mentioned before, and then we run the score, right? So the advantage of this is that obviously we can pre-compute all of these hidden states for all of the content. So as the search queries come in a real-time setting, for example, where latency actually matters, we'd only have to compute the hidden state, the embedding for the search query free ship 50. But since we're doing this content gaps analysis, you know, continuously in the background, asynchronously, we are not constrained by latency applications. So the cross-encoder, right, it works very similar. On an architectural level, the model, it's also simply a transformer encoder, right? There's no additional magic in there. The only difference is, instead of feeding the search query one time into the encoder, producing the hidden state, and then separately feeding the content in, we combine the two directly on the input level, right? We say free ship 50, then we have some separation token or even nothing, it's not that relevant. And then we put our content, right, to encourage customer engagement and so on, right? We tokenize the whole thing, we throw the whole thing at the cross-encoder, and then we get all of the hidden states for this combined together pair of text. And then we take the classification token, right, the hidden state again under the hood. This will also be some sort of vector. We slap some classification on top of that, and then we get one output. We take the sigmoid, so we get a 0, 1, right? And then 0 to 1 represents how similar those two things are, free ship 50 and the actual piece of content. So the classifier can also just be fully connected linear layer, no special magic there, right? Why does this work better, right? Why does the cross-encoder work better in this specific example? And the answer is very simple. It's the attention mechanism, right? So the main thing with transformers, and when they were introduced in the all you need is attention paper, or attention is all you need paper, was the attention mechanism, right? And just to remind you quickly, the attention mechanism basically allows us to dynamically model long-term dependencies between words within text, right? So in our specific case here, the presence of free ship 50 as the search query input allows the cross-encoder internally to understand, quote unquote, or to prioritize the part of the content that is actually connected with this free ship 50. In our case, it's a simple one-to-one match, so it's very easy for the cross-encoder to pick up that those are the same words, so probably there's relevance there. But in an enterprise setting, for example, right, the attention mechanism can capture relations like, let's say Jane Doe works in HR, so she's an HR employee. So we have content that talks about the finance department, the HR department, the R&D department, and the engineering department, and our search query contains Jane Doe. Our cross-encoder, through the attention map, can directly understand that of all of that content that discusses all of the departments, HR is the most relevant one, so the model should focus on only primarily those parts as it produces the output, because Jane Doe is an HR employee, right? That is if we actually fine-tune on company internal content, and we'll see later how we do this. And that's how we end up with here the cross-encoder doing much better with this free ship 50 promotional code. So the proposed methodology, right, is basically we have content, we have user search queries or user questions, throw them into cross-encoders, and then with this pseudo algorithm where we loop over all the content, we get search queries and questions for which we don't have content. And we can tell our customers, hey, look, here's the things people are looking for which there's no corresponding content within your knowledge base. And then, you know, they can prioritize which content they create based on that list. And this works great, even with pre-trained cross-encoders already. This works very well, provides a lot of value to our customers in terms of letting them prioritize which pieces of content they should actually focus on, right? They see, for example, oh, users searched a lot about the vacation policy, right? So, and we have certain things that are not listed there, right, in our documents. So we probably should go and write content about that. But in an enterprise setting, especially, or any sort of organization where you have internal keywords, internal naming schemes, and so on that are not public knowledge, the cross-encoder will sometimes not capture certain relationships, right? So, for example, John Smith works in HR, right? This is something that the connection between John Smith and HR-related content. So if John Smith appears in the search query and we have HR-related content, that's a good match. That's not obvious because John Smith working in HR is not public knowledge. The cross-encoder has never seen that knowledge, right? Similarly, our CEO within content can be a reference to Jane Doe, right? Because Jane Doe is the CEO of the company. And this link is not established within the cross-encoder. So we want to expose the cross-encoder to domain, industry, and customer-specific data. And that's why we fine-tune on customer data, right? To get additional performance and get better at detecting these content gaps for a particular organization. Because content gaps, as we saw, it's a very customer-specific or knowledge-base specific problem, right? Like the content that needs to go into Wikipedia is completely different than the content that needs to go into your technical documentation of a project that you're working on, right? So having something that's fine-tuned on that data is very useful. So what are the pain points with fine-tuning? You have a cold start problem, right? In most enterprise settings, content is always easily accessible. There are many SharePoint pages, there are many Confluence documents, there are many PDFs available, right, that you can easily access. But the search queries and the chatbot conversations are not that easily accessible, right? Gen AI use cases, especially in corporations, are still very limited. There's not a lot of conversational data available. And search queries actually exist, right? Because people search a lot of things on Confluence, for example. But it's not always that easy to extract those things out. There are not always APIs available to easily get access to the search queries. The content is usually much easier to export. So that's where synthetic training data generation basically goes in, right? It allows us to have only access to the content of a particular organization and still fine-tune the cross-encoder by generating synthetic search queries. And this is relatively simple, right? So again, this is a real example here. I ran this a couple of days ago, right? Using the same text as before about these promotional codes. You can throw this at pretty much any LLM. You instruct the LLM to generate 5 search queries that fit this piece of content and 5 that are similar but don't fit, right? And we see, here, I think this was run with GPT-4o Mini, one of the cheapest models out there, right? You can also run it using Llama 3.23 billion. which is a 3 billion parameter model, like very small. You can even self-host that. It's very cheap to run. Yeah, and it correctly generates promotional codes, discount codes, actually lists the 3 main codes that are listed within this, right? And then the negative search queries are similar to sort of promotional codes, but they don't actually fit the content, right? And we want it to be very close so that actually it's not that easy for the cross-encoder to learn it, because then the cross-encoder actually, during training, learns the harder parts of distinguishing what is a good match and what isn't a good match. So here we have loyalty program benefits, right? Sometimes they are connected to promotional codes, but there's nothing mentioned in the content, right? Same with customer rewards or cashback offers and so on, right? And, promotional codes might improve customer retention, but it's not mentioned in the content, so it's definitely not a match. So let's fine tune, right? Let's take this content here together with those search queries. Let's create these green pairs here, which are, positive pairs, right? So matches. And then we have the negative pairs, and they're not matches. Oops. What happens when you fine-tune a cross-encoder like this is, no matter of the content, if you put anything from this green box here, so promotional codes, discount codes, into the model, independent of the content, it will tell you it's a match, right? And similarly for stuff from the red box, the model has a tendency to say it doesn't match. The reason for that is simple. If you're not careful, promotional codes will be generated for this piece of content, so it appears in a positive context. And for example, loyalty program benefits appears in a negative pair. If those 2 search queries never appear in the opposite pair, so the negative one in a positive pair, and likewise the positive one in a negative pair, the model will have a tendency to bias towards just predicting the positive search term as matches always, independent of content. And the way you fix that is by diversifying the data set. So instead of just generating positive pairs from promotional codes and discounts, we also need to generate negative pairs, which means we need to find content for which there is no match with this promotional codes, right? And how do we do that? Well, for the top one here, to get a negative piece of content that doesn't match promotional codes, that is relatively easy, right? What you can do is you can just do semantic-based search, select randomly from outside of the top 50 results, right? Because if you do a search for promotional codes and you get your list of results and you pick something that's not in the top 50 results, there is a very high probability that it's not a match. It's a bit more difficult for the negative terms, right? Because for these, you want to create matches, right? It's not a guarantee that if you search for improving customer retention, that whatever is in the top 5, for example, search results, that's actually a match. If there's no existing content for customer rewards, for example, it might still return you some piece of content, but that piece of content might not be a good match. So you have 2 options here, right? The first is you run the cross-encoder and you select something that already scores high, right? And this is the more naive, simple approach, and it works. But the downside of it is that your cross-encoder already knows that something is a good match. So during training and fine-tuning, you're feeding it data that it already knows, and the only purpose of that data is so that it doesn't forget something that it already knows, the model, right? It's much better if you'd actually have some training data that teaches the model something, right? And here you can generate synthetic content that is a good match. And this is also a relatively easy problem, right? Basically, you need to feed an LLM these negative search terms that you've generated, like loyalty program benefits, and you ask it, please generate me a piece of like content within the sector that I work in, within this department, right, that matches the search query loyalty program benefits, right? And you can generate that multiple times, get various variants of it, and then you have these positive pairs for example, loyalty program benefits. And once you have that in place, you can fine-tune and everything works perfectly. Some other issues with the proposed approach, around 15%, this is real world, what we found to be actually the case on real customer data, is that 15% of positive search terms are not really that relevant, right? LLMs are not perfect. They generate noise. They get better with each iteration, right? But even if we went, let's say, from 15% to 10% to 5%, right? 5% of not relevant search terms is still not great, right? And the solution that we found here is that you can use clustering to kind of determine which search terms are sort of out of distribution, and then you can just discard those, basically the biggest outliers, and that kind of gets rid of maybe half of the irrelevant search terms, gets you from 15% to maybe 8-9% noise still. And then the second insight is that because we are generating these search terms synthetically, the removal of them and filtering, so removing this 15% of noise, can be very imprecise, right? We generate enough volume of search terms that even if we cut off half of the search terms, 50%, right, to reduce this 15% noise, we still have plenty. We can always rerun the whole synthetic data generation pipeline, right? Increase the temperature of the LLM, rerun again, you get slightly different search terms, and you can always filter and filter and filter them, right? You can stack more and more LLMs on top of each other to filter out the noise. And eventually you can sort of, what is realistic, at least what we found to be realistic, is that you can go from like 15% to sort of 3% noise if you stack multiple LLMs, right? You can use GPT for generation, then Llama for filtering. Then you generate with Llama, use GPT for filtering, right? And you do the same with the Anthropic models and so on. And each model contributes slightly different search term and validates and filters slightly differently. So this was the positive search term. And then for the negative search terms, we found that a lot of them are too irrelevant to actually help with the training. And there's no real downside except that you're going to waste time feeding data to the crossencoder that the crossencoder already knows is not a good match. And the way you filter those out is you do some semantic retrieval or semantic search. And if for a given search term already the content is not in top n, and n is just a hyperparameter, one of the ones we found works well for us is top 100, top 200, top 300, that sort of range, then you just drop that search term, right? Because if semantic retrieval already determines that this is not a good match, the crossencoder will most likely already know that as well, right? So it's a waste of time and compute and energy to feed that training data to the crossencoder still. So what are some real-world metrics that we found with these content gaps? So some caveats first. This is very labeling dependent. You use a different labeler that is a bit more lenient, a bit more liberal with what is missing and what isn't missing. You get very different results. So it's very hard to benchmark this problem. And it's also very sector, customer, and domain dependent. So you have high variance. So what I'm showing you here are the averages across all of our customers and sectors. So be aware of that. In some cases, it performs significantly better, in some significantly worse. So at 0.9% threshold, we're able to find 35% of all content gaps at sort of 95% precision. And the reason I'm showing such a high threshold here is because this is a way that we can basically give our customer a list of topics that they should invest in, right? And we can say 19 out of 20 of the topics on that list are things that you aren't covering yet with your knowledge base. So go write that content. And don't worry, 95% of those predictions are actually accurate. And then at 75% threshold, we have basically nearly double the recall, and we're looking at 85% precision, which is also quite interesting. What I think is much more interesting here is how much does the synthetic training data generation actually help, right? This track here is called application of LLMs or usage of LLMs, right? So generally speaking, for us, we found that fine-tuning using the synthetic training data increased our crossencoder ROC area under curve by more than 10% across multiple data sets and customers and in various industries, right? So the only thing we really had to do was send all of our content to a bunch of LLMs, generate some search queries in a reasonably smart way. There's a lot of prompt engineering and prompt optimization under the hood. And once we get that, right, we have an automated pipeline that allows us to fine-tune these crossencoders that just, for practically no money, right, just the cost of the LLM and the fine-tuning cost, which for most of our customers is sort of $50, $60 for the whole pipeline. We get 10% more area under curve for the ROC. And it's similar for the precision recall curve, AUC as well. So I want to leave you at the end with some additional interesting thoughts and directions that I didn't cover in the talk before we go into question and answers. So what we covered is content gaps, right? Which is relevant, non-existing content. Our approach, our pipeline, and using this cross-encoder and the algorithm that I've showed you, this pseudocode algorithm, we're also able to determine what is relevant existing content. So instead of telling our customers what are content gaps, we can tell them what is the most relevant content with you in your knowledge base, right? And this allows them to prioritize which content they should work on that they already have, which content they should improve, which content they should boost in search. And the rest of the content, right, they can potentially archive, they can deboost it in search, potentially even remove it if it hasn't seen any traffic at all. Then I also mentioned extending to conversations instead of using search queries, right? I mentioned 2 proxies for relevant content, and one of them was conversations. We didn't touch that yet. So it's a harder problem, generally speaking. That's what we found, because generating synthetic conversations is hard, or at least harder than generating search terms. It takes more tokens to generate that, and it's more compute as well for fine-tuning. So here I just want to offer you one first stage simplification to think about, and this is how we internally approach the problem as well, which is that first we built a conversation to search query generation pipeline, right? We took conversations and we tried to generate 2 free search terms or search queries that kind of capture what the user in the conversation wants to do, right? Let's say the user asks about, hey, I'd like to refund the order that I did, right? Because the package arrived broken, right? So we would generate refund order as a search query. And then you can just reuse the existing pipeline that I showed today to assign a target to that conversation, right? You can say the search query refund order is a content gap or it's not. So ultimately, for the whole conversation from which you generated the search query, you know whether it's a gap or not. And then you can bootstrap the synthetic training data generation using this method. If you can generate realistic conversations, you are basically done at that point, because you do not need to generate or assign labels, because you can assign them via this search query generation proxy, right? Okay, and that's it from my side. So I'm happy to take some question and answers in the last couple of minutes. And
yes,
please don't forget to leave feedback.
Thank you very much, Timo. We literally have 3 minutes, and there are 2 questions essentially. So I will read them, and please address them as briefly as you can. Are there any cases where cross-encoder does not work better than dot product? If so, could you give any examples of those? And the second question, I think you actually largely addressed that. Would you say that it is viable to have some absolute score threshold like 0.9 to decide whether the document is relevant or not? So maybe a couple of more ideas if you want to underline something here as well. So please take literally 2 minutes, and then we have to switch to another.
Yeah, so the first question is, the answer is generally no, right? So the cross-encoder internally, if you fine-tune it in a specific way, it can even replicate fully the dot product method, right? Because underneath the architecture is very similar, and at the end, the linear layer could even be the dot product or something like this within. You could have the dot product represented within the cross-encoder, right? Yeah, so that's the first answer. And the second thing is, yes, we select very high thresholds and some lower thresholds in other situations, depending on who consumes these content gaps, right? So when we present the list of content gaps to content creators within organizations, right? Like, for example, the person responsible for writing the HR policies, right? We select a very high threshold because precision is important. Recall is not that important. When we try to give a visualization, for example, of all the content that is present and all the content that's missing within an organization, for example, let's say to higher level, stakeholders, right, management, then we select the lower threshold because the precision is not that important and recall becomes slightly more important again, right? So that's why I showed also 2 thresholds in the real world metrics. Basically, one is for like, here's your list where we're absolutely certain that these are content gaps. So go invest time, go invest resources, go write content for these search terms, right? And then on the other hand, it's a bit more, okay, here's what we think are content gaps, right? We're very certain for most of them, right? But 15, 20% are still sort of like wrong within that. So it depends on the use case, and we do use different thresholds, yes.
Okay, great. Thank you very much. There are many thanks on the chat, so I think everybody liked your talk very much. So thank you very much once again, Timo. And yes, to our guests, let's see each other on the next sessions. Thank you, and have a good day.
Thank you very much from my side as well.